Speaking of sand and ceramic,
Oh yeah.
we're going to talk about network solids.
Yay.
Hey, in a network solid, it's a molecule that has all covalent bonds. Now, interesting thing about this, of course, we've talked about this. Covalent bonds are the strongest of all bonds. They have a strength of 100.
Yes.
So and these only applies to two varieties of elements.
Yes.
Two elements. This only applies to carbon
Carbon
and
sulfur.
silicon.
Oh, silicon. Sorry, not sulfur.
You're still awake.
I know.
Still asleep.
It's an S element.
All right. The examples of this are diamonds. I'd love to show you diamonds, but I don't have one. My wife has a diamond. Diamonds,
They are a girl's best friend.
graphite, quartz. These are the big three to remember for these things. And sand, Mr. Sams was just talking about. Sand, of course, is quartz, silicon dioxide, and has a very, very high boiling point and melting point, too, for that matter. All right. So diamonds here. And this is graphite. Graphite, by the way, is in a pencil.
Yep.
So,
Now,
go ahead.
real quick, diamonds very, very hard.
Yes.
Okay, and those are held together by these tetrahedrally arranged carbon atoms, and so that's very strong. A force value of 100, like we were talking about. Now the graphite, notice they're held together in these sheets. The sheets are kind of cool. You've got these little hexagons that are stuck together, and graphite, it's kind of slippery. That's why your pencil moves across your paper. It's because those sheets kind of stack on top of each other. They don't attract to each other really well, so they slide across each other, which is what makes graphite slippery.
And the weak bonding of the layers is held together by London dispersion forces.
Yeah.
That's why when you write with a pencil, it's going to come off on the paper, but it's very, very strong, sticking in the flat plane.
Like locks in your doors, they use graphite as a lubricant. They just shoot it in there and it makes it all slippery.
Yeah, it's very, very cool.
Yeah. There's actually one other allotrope of carbon, too, that we don't really talk about a whole lot. And that's called buckyball.
Yeah.
And it basically looks like a soccer ball.
Yeah.
They're actually doing a lot of research with it now, of like putting things in the buckyball and using it to deliver things in really small quantities.
Yeah. So here, folks, interesting picture. This is actually Mr. Sams was talking about a buckyball, and this is the structure of the buckyball. These are all carbons held together in a they're sp2, aren't they?
I don't know. I actually haven't.
They're all held together by three.
They're
There's
not really
three.
planar though, so I'm not sure.
Yeah. Anyways, but that's what
we're not
buckyball
sure.
looks like.
Yeah, these are also called fullerenes. The person that came up with these, Buckminster Fuller. So Bucky from Buckminster, or fullerenes from his last name.
Yeah. So yeah, that's kind of cool, I think.
Yeah.
So that's the buckyball. So I think it's intriguing to kind of look at that. All right, and graphite again.
There's your graphite
Yeah.
letters.
And then actually, let's take a look real quickly. This is the silicon oxides are the ones that primarily. There's a number of varieties that they call silicates. Some of these are silicates, and then
tetrahedral.
Yeah, and then you've got S's and O's basically, and the S I believe is the yellow. Yeah, and then the red is the oxygen in this picture. So
So
if you
that's
see
all
SIs and O's, you've got a network.